Okay, we're going to start our last chapter. It's on solids and liquids. And the reason it's the last chapter is because we really have to draw on everything we've learned this block in order to understand. We need to be able to do Lewis structures, VSEPR geometries. We need to be able to do thermochem and understand delta H's. We need to be able to do stoichiometry. So we will pretty much be summarizing the class, and you could almost think of this as a review for the final if you plan on taking it. So we are only going to do the first 5 sections. So we're not going to do the sections on crystal structure. It's important and it's interesting, but I always have to choose to leave something out because we really can't do it all in 107. So we will leave out those sections. So we're going to talk about intermolecular forces, properties of liquids, phase transition, phase diagrams, the solid state of matter, and then we'll skip that lattice structures and crystalline solids. This is just a picture to get you thinking about solids and liquids. So dry ice, carbon dioxide as a solid, it goes straight from the solid to the gaseous phase, never goes through the liquid phase at atmospheric pressure. So that's something very different. I mean, water goes from solid to liquid to gas. So thinking about the properties of dry ice will help us understand the intermolecular forces, or the forces holding molecules in the solid phase of CO2 that lead to the properties that make it unique. So intermolecular forces, these are the things that will take us back to Lewis structures and VSEPR geometries. So when we think about, if you have water in the liquid phase, it's held together by the interactions of one water molecule with another water molecule. And so those are intermolecular forces, the forces between molecules. So when water goes, for example, from liquid to gaseous phase, you don't change it into hydrogen and oxygen. All you do is break those intermolecular forces and take a liquid water molecule and put it into the gas phase. So we're going to describe the types of intermolecular forces possible between atoms or molecules in condensed phases. And these are going to be dispersion forces, dipole-dipole attractions, and hydrogen bonding. Then we're going to identify the types of intermolecular forces experienced by specific molecules based on their structures. So that's where we'll trace it back to whether or not a molecule is polar, and basically try to understand how strong the forces are that hold molecules next to each other. Then we'll explain the relation between intermolecular forces present within a substance and the temperature associated with changes in its physical state. So why is it, for example, that ethanol boils at a much lower temperature than water does? Things like that will be traced back to the forces in between molecules, therefore to the structures of molecules. So, intermolecular forces, IMFs, the various forces of attraction that may exist between the atoms and molecules of a substance. They're a result of electrostatic phenomena. So they're a result of plus and minus being attracted to each other. And they're not covalent bonds. They're interactions. They're going to be weaker than covalent bonds, easier to break. So we want to make sure we call them forces and we don't call them bonds. So kinetic energy provides the energy to require or to overcome these intermolecular forces. So for example, if you're trying to boil water, it doesn't start to boil until it gets to a temperature at which there's enough kinetic energy in the liquid water molecules to allow them to break free from each other. So to have enough kinetic energy to overcome the forces that hold them together. And intramolecular forces, these are the forces that hold atoms together in a molecule. So those would be, if you think about the water, it would be the hydrogen-oxygen bonds in water, which are covalent bonds. Those are intra forces, or bonds within a molecule. And we're going to be more focused on inter forces between molecules. So the differences in the properties of a solid, liquid, or a gas are a result of differences in the strengths of the intermolecular forces that make up each substance. So not so much true for a gas, because when you think about a gas, the particles are so far apart they don't interact. So we were able to do the chapter on gases, because in general, if you're assuming gases are a deal, then you don't have to worry about the intermolecular forces. So this is just a picture reminding us of the phases. A solid on the left does not fill the container. It's very different even than a liquid. A liquid will cover the bottom of the container, and then a gas will completely fill the container. So when you think about the structures of solids, liquids, and gases, they're very different. But in both solids and liquids, the particles, molecules, or atoms, whatever it is that makes up the solid and the liquid, they're close enough together that the intermolecular forces are extremely important. Whereas when you look at the gas, this is exaggerated how big the gas particles are, but they're far apart. And so the intermolecular forces that will result aren't very important because the molecules aren't really close enough together to experience those forces. So these are just pictures and remind us if you put a cold drink on the table, if there's water in the atmosphere, Colorado Springs doesn't have much. Maybe if you're in a more humid climate, you'll see that condensation on the outside. So that's because as you've lowered the temperature and the air is hitting it, it can no longer hold as much water vapor, so it condenses as a liquid. It's the exact same thing that happens with fog. That's a result of the temperature coming down and the water molecules in the air condensing out as liquid. This is a picture to remind us that whether or not something's a gas or a liquid depends on the temperature. So in this picture, where the temperature goes down, the gas water molecules condense to liquid. But it's also true, it depends on the pressure. So butane would be a gas if it was at room temperature and just open. But when you have it inside of a lighter, you have it at a higher pressure. When you have a higher pressure, we'll see pressure is related to the temperature at which something vaporizes. So pressure and temperature both are important when you think about whether or not something will be a liquid, a gas, or a solid. So the strength of the intermolecular forces vary with different substances, and we'll go back and look at molecules to understand what that means. All are significantly weaker than intramolecular forces, which are the covalent bonds. And we have three types of intermolecular forces to worry about. First one is called a dispersion force. Second is a dipole-dipole attraction. And the third is a hydrogen bond. So the intermolecular forces above are sometimes collectively referred to as van der Waals forces. So if you think back to the gas law chapter, when we got to a situation where we had a pressure and temperature at which our gas didn't behave ideally, where the interactions were important, we called that the van der Waals equation of state. So it's a reason why these are van der Waals forces. These are taking into account the interactions between molecules. So when we look at something like HCl, and we look back at what we learned about polar molecules, we know that HCl is polar because chlorine and hydrogen have different electronegativities. So the end with the chlorine is slightly negative, and the end with the hydrogen is slightly positive. So if you have them sitting next to each other, the slightly positive hydrogen end will interact in a favorably way, intermolecular force, and that will be attracted to the slightly negative chlorine end. So dispersion forces will be the first one we talk about. All substances, whether they're polar or nonpolar, have dispersion forces. They're also called London dispersion forces. And the constant motion of electrons in molecules and atoms result in instantaneous dipoles. So remember when we talked about quantum, and so we even have to think about when we talked about molecular orbitals, if you have a probability in a molecule of where you're going to find the electrons, you can find it in that whole region. And so at any instant, you might find it on the right-hand side, the left-hand side. So you'll essentially have a slightly negative or positive side to that molecule just based on that probability distribution. And as soon as that happens, the molecule sitting next to it is going to have its electron cloud distort so that it's attracted to the instantaneous dipole in the first molecule. So if the first molecule has a slightly negative right-hand side, then the molecule sitting next to it will create a slightly positive side on the left-hand side so that they can interact. So that's an induced dipole, a dipole that's created by the electron cloud being distorted by other charge. So both of these fleeting temporary dipoles result in a weak electrostatic force known as the dispersion force. So this is just a picture of that. So just looks very similar to this one, except that this is not permanent. So here, that's a permanent dipole. Chlorine always has a little more probability of having electrons near it than hydrogen. Whereas now, if you actually have a neutral molecule, but if you have one molecule have a temporary dipole, the one sitting next to it will have an induced temporary dipole, and then those slight negative and slight positive ends will be attracted to each other. But that's flowing through your system, changing all the time because these are temporary dipole moments. So heavier molecules and atoms will exhibit stronger dispersion forces than do lighter molecules and atoms. And this is because larger atoms have greater polarizability due to the valence electrons being farther from the nucleus. So polarizability, if you think about something like a helium atom versus a xenon atom, they both don't have dipoles, they're just neutral atoms. But if you allow the helium to see a charge someplace, its electrons are held really tight because it's a very small atom, and so it's going to be harder to slightly polarize it, make one end positive or negative. Whereas if you look at the xenon, the electron cloud is much, much bigger. And so if there's a slight electric charge someplace, it's going to be easier to distort the electron cloud around xenon because those electrons aren't held so tightly to the nucleus. So the larger atom would have stronger dispersion forces because it's easier to polarize. So polarizability, the measure of how easy or difficult it is for another electrostatic charge to distort a molecule's charge distribution. So it really depends on how tightly those electrons are held to the nucleus and how easy it is to influence them with some other charge. So this is just a table of the boiling points and melting points of the halogens. So we have fluorine, chlorine, bromine, iodine. So this is going down a group. And notice that the boiling points just increase. So fluorine, diatomic, chlorine, all of the halogens as diatomic are completely nonpolar, but they do have these London dispersion forces. And the bigger the molecule, the easier it is to distort that cloud. And so the melting points and boiling points increase with the molar mass and the atomic radii of each of those systems. So you have stronger dispersion forces lead to higher melting and boiling points, higher temperatures, and therefore more kinetic energies needed to overcome the intermolecular forces. So if it takes a higher temperature to melt or boil, that means that you need more kinetic energy to overcome the forces. So they must be greater forces, stronger forces. So this is a picture of how if you have methane, I think the second one is silane. I don't know if the other two have names, but this is down a group, carbon, sulfur, germanium, and tin. And when you put 4 hydrogens on each of those, they're completely nonpolar, they're tetrahedral. So we'd have to know that these are nonpolar molecules. And the temperature of boiling is increasing. Is this the, I don't know, I guess I don't know the boiling points. Boiling or melting is increasing as you go down a group. So not only do dispersion forces increase with the size of the atom, they also increase as you change the shape. So you can have a molecule that has the same number of carbons and hydrogens in it. And remember, you can add them together in different ways to make different structures. And then we call those isomers. So when we look at these, you notice that, for example, on the right-hand side, if you have normal pentane, if you have just a single long chain of carbons and hydrogens in every place that you'd need one to give 4 bonds to each carbon. Those two molecules can stack next to each other, and there's a lot of surface area. So there's a lot of area for them to be attracted to each other. Versus if you look at these other two structures, which also have the same number of carbon and hydrogens, there isn't as much surface area. So even though these have exactly the same number of carbons and hydrogens, so the same mass, the one that has the structure that gives them the most surface area to interact on the right, the normal pentane, is going to have the higher boiling point. This is a little discussion in your book about how geckos stick to things so they can walk right up glass and stuff. And they have these little structures on their paws that can form dispersion forces with the surface. And that's how they're able to stick. They don't have suction cups or anything. They just use the London dispersion forces. So the second type of interaction are molecules with permanent dipoles, and they display dipole-dipole attractions. They're present only in polar molecules. Dipole-dipole attractions are stronger than dispersion forces, and polar molecules contain dipole-dipole attractions and dispersion forces. So adjacent molecules line up such that the partial negative pole of one molecule is as close as possible to the partial positive pole of the other molecule. So this is a picture of that. So if you look at molecules in a structure where these are permanent dipoles, where one end of the molecule is partially positive and partially negative on the other end, so this would look like HCl, for example, then they're always going to be lined up in such a way that their plus and minus can be attracted to each other. And so those are the forces of a dipole-dipole attraction. So comparing polar and nonpolar molecules of similar molecular weight, if we want to do that, the presence of the stronger dipole forces in a polar molecule leads to a smaller to moderate increase, or to a small to a moderate increase in the boiling point. So this dipole force tends to be stronger than the dispersion force. The very last one is hydrogen bonding. It's only present in certain polar molecules. So it's really a very, very, very polar dipole-dipole. It's unusually strong type of dipole-dipole attraction. Hydrogen bonding is the strongest van der Waals force. And you need to have a hydrogen covalently bonded to either nitrogen, oxygen, or fluorine. Those are the three most electronegative elements. And so, yes, when we look at this, so let's think about water. Water has a hydrogen bonded to an oxygen, and therefore it can hydrogen bond. When you think about it, if you have hydrogen, it only has one s electron, and then you have oxygen. And if oxygen is so much more electronegative that it's pulling those electrons in the bonds closer to it, you're leaving behind a hydrogen that has no electrons really. And so it's a very small positive charge. And when you look at how the hydrogen bonding takes place, on each of these oxygens, there are two lone pairs. It's almost as if the hydrogen on one water molecule is forming a new bond with a lone pair on an oxygen molecule of another water molecule. So it makes a very, very, very strong interaction, which we call the hydrogen bond. So hydrogen bonds are strong intermolecular forces due to highly concentrated partial charges. You have a large difference in electronegativity between the hydrogen and the atom it's bonded to, and that creates that large dipole. The very small size of hydrogen and relatively small size of fluorine, oxygen, and nitrogen make those charges on them more concentrated because the particles are smaller. This is an interesting picture. It shows you within the group. So if you have, for example, going down the sulfur group or the halogen group or the next group, let's look at the top one. So if you're going from hydrogen sulfide to the next with selenium and then tellurium, the boiling point is increasing slightly with each, and that's because the molecules are getting bigger, and therefore the dispersion forces are stronger. So the dipoles are getting smaller because as you go down, the electronegativity difference isn't as much. So it's the dispersion forces that's creating this increase. So we'd expect where these question marks are, that water would be the top one. And then the green one would be ammonia. And what would this one be? HF. And so that's where you would predict them based on how the others change. But when we look at it, each of those can form hydrogen bonds. So water, HF, and ammonia, they can all hydrogen bond. And so notice the trend is totally the opposite, that it's the hydrogen bonding that makes their boiling point so high. Even though they're the smallest molecule, their London dispersion forces are much weaker than the others. But that super strong dipole-dipole of a hydrogen bond changes that trend. This is just talking about DNA, and DNA is a double helix, and those two strands of DNA are connected by hydrogen bonding. In order to then take the information from your DNA, your body has to break those hydrogen bonds and break apart those two strands, and then it can reproduce those. But it's hydrogen bonding that makes it a double-stranded molecule. And this just shows you a picture of that hydrogen bonding. So there's a lot of nitrogen, oxygen, and hydrogen. So as you look at this, the dotted lines are the hydrogen bonds, the solid lines are covalent bonds, and that's just showing you how those hydrogen bonds are holding the two strands together. So properties of liquids. We can distinguish between adhesive and cohesive forces, define viscosity, surface tension, and capillary rise, describe the roles of intermolecular attractive forces in each of these properties. So for liquids, honey is very viscous. Oil is very viscous. Other things like water, ethanol are very low viscosity. And so viscosity is a measure of the resistance to flow. So if you have high viscosity, you flow very slowly. So when you're trying to put honey on a biscuit, sometimes you get hungry just waiting for the honey to come off the end of the honey stick. And also when you pour oil into your car, it's very slow and moves very slowly. Attractive forces result in a spherical water drop that minimizes surface area. So that's because of the cohesive forces. So cohesive forces are the forces that hold molecules together in a system. So in a system of water, the cohesive forces are the forces of the hydrogen bonds holding one water next to another. And if you think about it, if every molecule in the interior of the water sample has water molecules all around it interacting, when you get to the surface, you're missing interaction on that top side. And so that increases the attraction of the molecules for the inner molecules, and that gives you that surface tension that gives you water droplets. Surface tension prevents this bug from sinking because it's the water molecules are pulling in and you have a surface that is very hard to break. So the differences in the relative strengths of cohesive and adhesive forces results in different meniscus shapes for mercury and water. So water has an adhesive force between glass. So that means it's attracted to glass. So cohesive force is the force that holds molecules to each other. Adhesive force is the force that would, in this case, be the water or the mercury interacting with the glass tube. And so the water has very strong cohesive forces, and mercury, or the water has strong adhesive forces. It interacts with the glass, and so it's attracted to the glass and tries to interact. So it tries to basically have more surface area of interaction with the glass, whereas mercury is the other way. It's got stronger cohesive forces, so it's more attracted to itself, and so it doesn't attract itself to the glass and move up the glass, trying to maximize that surface area. Capillary action is the action of cohesive forces, adhesive forces, and then gravity all working together. So gravity is pushing this liquid down on the left. The adhesive forces are pulling it up with the molecules, and then the cohesive forces are keeping it down because they're the forces that hold molecules with each other. So a playoff of all three of those will determine how much capillary action you have, how much the liquid flows up whatever surface it's on. That's just a picture of that process. This is just an example. When you're giving blood, they always use a little tube, and so that's capillary action. How high the blood goes up the tube depends on the surface it's creating with the glass, the cohesive forces it feels with itself, and then the force of gravity holding it down. Okay, so the next discussion is about phase transitions. This might be, let me see. I think I'll do a couple more, sorry. We don't have too many slides in this. Let's go through about 5 more slides. So phase transitions, so that's a very important property of solids, liquids, and gases. So we want to define what it means to say you have a phase transition, explain the relationship between a phase transition temperature and the intermolecular forces that are holding molecules in the phases, and describe the processes represented by typical heating and cooling curves, and compute heat flows and enthalpy changes accompanying these. So the heating and cooling curves are experiments that you can use to determine where phase transitions are in terms of temperature and pressure. So we're going to talk about vaporization and condensation. They're the opposite of each other. Vaporization is going from liquid to gas. Condensation is gas back to liquid. Melting and freezing. So melting is going from solid to liquid. Freezing is going from liquid to solid. And then sublimation and deposition are the opposite, in that sublimation takes you from solid straight to gas, and deposition takes you from gas right back to solid. So when we talk about vaporization, liquid is converted into a gas. In an open container, that vaporization continues until all the liquid is converted into vapor. So if you leave your water bottle in the classroom for a couple days with the lid off, you will come and find that all of the water has evaporated or vaporized. But if you have a closed container, then the process of vaporization is countered by the process of condensation. So as the liquid vaporizes, if it's held in a container where it has to stay above that liquid, the vapor does, then the vapor molecules are bopping around. As they hit the surface, depending on the temperature, they may not have enough kinetic energy to get back off the surface. So the double arrow represents that you reach a point where you have a constant rate for the liquid leaving the surface and for the vapor condensing back onto the surface. And so that double arrow represents a dynamic equilibrium where the amount of liquid and vapor stops changing, but which molecules in the liquid or the vapor phase continues to change. I think they meant where that question mark is to have that dynamic equilibrium double arrow. So when the rate at which the liquid vaporizes is equal to the rate at which the vapor condenses, a dynamic equilibrium is established. The liquid level in the container does not change after equilibrium is established. So for example, if we have bromine liquid, it will be in equilibrium with its vapor at some point. And after equilibrium has been reached, the number of molecules in the gas phase doesn't change with time. Therefore, the pressure exerted by the vapor over the liquid remains constant, and therefore we have a name for that. The pressure of a vapor in equilibrium with a liquid is called its vapor pressure. So remember, this only happens in a closed container, because if the vapor is allowed to leave, then it's not going to ever reach an equilibrium because it won't condense again. So this is a picture of the manometer we saw in our gas chapter, chapter 8. And we can use a manometer. So you start out with some liquid in your bulb and you allow it from B to C to be in there long enough so that it's finally in equilibrium with a certain amount or a certain pressure of gas above it. And then you can just use that manometer to measure what that vapor pressure is. So the pressure of a substance is independent of the volume of the container, and vapor pressure does depend on the intermolecular forces of the substance. So whatever pressure you end up at here doesn't matter how big that container is. You will have more molecules in the gas phase, but the pressure will be the same. So the vapor pressure depends on the intermolecular forces, and therefore the vapor pressure also depends on the temperature. So it's always true that as temperature goes up, the vapor pressure increases for anything because you have more energy available to keep the gas or the particles in the vapor phase rather than in the liquid phase. So there's more energy to overcome intermolecular forces, whatever they are. Substances with the highest intermolecular forces are going to have a lower vapor pressure because it's going to be harder to break apart the intermolecular forces. So you're going to have less going into the vapor at any one temperature. These are just some examples which we'll go through in class. You would predict, they want you to predict which has the highest vapor pressure. The highest vapor pressure should be the one with the weakest intermolecular forces. So it should probably be the dimethyl ether because it just has dipole-dipole forces. The other three all have hydrogen bonding. So ethylene glycol has the ability to do 2 hydrogen bonds. So that probably has the smallest vapor pressure. And then after that would be ethanol and then water. So the vapor pressure of a liquid always increases with increasing temperature. I said that just a second ago. And that is because the higher the temperature, the more energy, more kinetic energy available to break those intermolecular forces and take a molecule from the liquid phase and put it into the gas phase. So it will always be true, doesn't matter what the substance is, that the vapor pressure will change with temperature. And that's because of this. So as the temperature goes up, the average kinetic energy goes up. And so if the average kinetic energy goes up, you're going to have more molecules that have enough energy to escape the surface of the liquid, because that's dependent on the intermolecular forces. Okay, now I think we can stop there and we'll have one more short lecture on chapter 10.